Hey guys, welcome to DEFCON 20. So, what are we here to talk about? I got some good news, I got some bad news. Good news is, we are actually going to fix this thing. Who here focuses on blowing stuff up? Who here's offense, hack some stuff? Yeah, you're awesome. We need you. Defense doesn't have offense. You know what happens? Defense gets stupid. We call that compliance. The bad news is we're not going to fix it by doing things the way we've been doing them for 20 years because look where that got us. There's a lot of dogma in security, and the dogma is useful because there's a lot of really, really crappy stuff that we shouldn't be doing. But that doesn't mean what we're doing today is entirely correct. Got a riddle for you. What is the fundamental difference between offense and defense, between an attack and a defense? You can tell when an attack doesn't work. Offense has a quality filter. Put up or shut up. Either it works or it doesn't. That doesn't mean we don't get crappy attacks floating around out there. I don't know if you've noticed, there's a bunch of them. But it's not the same. It's not like it is in defense. Defense has a lot about dogma. It's not much science. We've kind of transmuted the, well, you can't defend against everything into, I don't need to show what I do and don't defend against. And critiques against defenses don't need to show how useless they actually are. So we have this really random discussion with insufficient skepticism. So that's really what this talk is about. This talk is about doubt. This talk is about calling bullshit. If you walk out of this talk believing everything even I have to say, you're doing it wrong. Guys, my goal is to show you some new ideas. And they're out there. They're, by normal theory, wrong. If they are wrong, let's find out. Let's prove it. But let's not just assume because it violates dogma that it might not actually be a better path to protecting these networks. So just to talk concrete, here's a fundamental test. You take 2,000 machines with a given defense. You take 2,000 machines without. You come back in 6 months. You see, is there a statistically significant difference in the infection rate? Now, I'm not saying that everything, and even in the near future, is going to be tested like this, but let's at least recognize a gold standard when we see one. One of these days, we're going to be spending as much time and money on security research as we are on medical research. Now, I don't know if you realize this, it took hundreds of years for medicine to get its scientific act together, and they had dead bodies. We got just like, an economy of a world or something at stake here, which, kind of matters. We got to fix this stuff. We don't have hundreds of years. We got to start fixing it fast. So we got 3 heads to the security hydra. 3 reasons why we're in this place. 1, we can't authenticate. 2, we can't write secure code. 3, we can't bust the bad guys. We're not going to talk authentication today because that's DNSSEC. And, well, if you want to talk to me in that in private, you can do that. We're not going to talk about busting the bad guys. I don't know if you noticed, but there seems to be some lack of consensus on who the bad guys are. I tend to worry about that time the entire Fortune 500 got owned. Aurora was really bad. People seem to forget about it. They're like, Stuxnet, Stuxnet, Stuxnet. I'm like, how about the entire stock market? I'm kind of worried about these small businesses that are getting their payroll stolen and their bank saying, sorry, your fault. That's what makes me worry. But other people are worried about, I don't know, Dark Knight Rises. So what are we here to worry about? We're here to talk about the inability to write secure code. Now, just inability, let me clarify. It's not that it's impossible to write secure code. It's not impossible to make an authentication system with certificates using the X509 protocol. It's not impossible to go out and bust criminals and bad guys. It's just not going to friggin' happen. It's totally improbable. Possible's not enough. Not if you want to actually say you fixed the problem. I wish I could just blow stuff up. It's a lot of fun. I do it from time to time. but I'd like to be working on different stuff 20 years from now. New bugs instead of the same existing ones. So what are we going to do today? We got 5 different things to talk about for DC20. We're going to talk about addressing timing attacks. We're going to talk about generating random numbers. We're going to talk about suppressing SQL injection attacks. We are going to detect network manipulation, a little bit of follow-up to neuter from last year. And just for fun, we're going to go scan the internet really fast. These are all things that are totally possible today. How do we make them more deployable, less expensive, more probable? Let's talk about timing attacks. Timing attacks are a lot of fun. Basically, generally when we model the security of a system, we look at who says what to who. And we never look at when. Sometimes when a message is sent leaks internal information that allows you to break the security of a system. Now, the timing differences we have on computers tend to be small, except for databases. They'll have like second-level deviations. But it doesn't matter. According to a really interesting paper, we can distinguish 15 to 100 microseconds of latency over the internet, all the way down to 100 nanoseconds of latency over a LAN. Just like 1,000 probes. I mean, this is a really small thing of saying, did that take 1 second, or did that take 1.0000001 seconds? And you can tell reliably. It's kind of cool. So Nate Lawson and Taylor Nelson did, I think, the best talk on this subject, where they looked at string comparison functions and broke a bunch of, they broke OpenID and OpenAuth, a couple of authentication protocols, really nicely. So the canonical correct fix to timing attacks is you make everything take the same amount of time, the maximum amount of time any individual comparison would take. And this is this neat little trick. It involves using XOR, and if when you compare values, you go through the entire string and you XOR everything around, you'll find out if there's a difference or not, and the time will not vary. Job done, move on to the next bug, right? I have never met anyone in my life who has ever implemented this. The problem is that if you want any security advantage, you have to do it every time there's a security critical comparison. That means you need to identify the security critical comparisons. You don't get to do this all the time because it is, by definition, quite a bit slower. And the difficulty of identifying all the circumstances where you need to do this stuff is enough to make this fix possible, but not probable. So what can we do instead? I seem to note that when we're up against internet level latency, the internet is slow, sometimes packets take longer to arrive than others. I note that now we can only distinguish 15,000 to 100,000 nanoseconds instead of 100 nanoseconds. That's 3 to 4 orders of magnitude. And internet noise is not random. It turns out you can just tell Linux on your network interface, be as slow as the rest of the internet, and it'll do it. It's a one-line command. Now, here's the deal. This is a lot easier to deploy. And it turns out that matters. I could probably get someone to go ahead and say, make things take 1 million to 3 million nanoseconds longer. I can't say make it take another second, but another 100th of a second, I might be able to ask for that. Now, who here thinks they know about this enough to say, bullshit, this is never going to work? Maybe someone. Here's the deal. Let's say this didn't work. I got some code to show you. This code right here is from the middle of OpenSSH. And what OpenSSH is doing is it's going ahead and it's comparing the password provided by the user through an encryption function to the password stored on the hard drive. And it's doing it in non-constant time. If the first character is right versus the 8th character is right, it's going to take a different amount of time. Now, the difference is going to be like a nanosecond. Like, it's going to be like one motion of the CPU. If you can find every single timing attack, if you just get enough samples, then I just dropped me some OpenSSH O-Day. Either my attack works, which it doesn't, or I'm onto something with this defense. Now, what we're actually looking for, what the actual equation we would want to have is how much timing noise of what nature will permanently obscure how much timing signal beyond the point of infeasible return. look, if I delay it a day, you're not going to find a nanosecond. So somewhere between a day and 1 nanosecond is an amount of noise that you can insert on a network interface that is going to destroy an entire class of security vulnerability with a single command. That is kind of cool. I like that. Now, there are things that can go wrong with this particular implementation using the single line to Linux. It was not really designed to implement a random value precisely between 1 million nanoseconds and 3 million nanoseconds. So maybe there's quantization. Maybe it's chunky in its delay. Maybe the noise pattern is wrong. It's Gaussian, which should be uniform, or uniform when it's Gaussian. Maybe the fact that other protocols, like TCP, it has its own timestamps. So every message that's sent out of a network interface actually has a thing that says, I was sent at this time. So even though the interface is delaying it, there's actually bits in there that say when it was sent. Maybe that's a problem. These are all things that can be fixed. The question is if it's worth investigating. And the deal is, our perfect fix, constant time comparisons, is the enemy of the good. As long as we think we have a fix and we're done, there's no reason to look for something we can actually deploy. This pattern shows up elsewhere. Let's talk about that time RSA was broken. No, not the time RSA was broken where the smart cards leaked their private key, or the time RSA was broken where the secure IDs were stolen by China. No, what is this, like, beat on RSA year? Like, it just keeps happening. No, what this time I'm talking about was some work by Ariane Lunstra and James Hughes, and also by Nadia Henninger, where they found that 1 out of 200 cryptographic keys on the internet were actually badly generated. This is a tremendous number. I mean, you got to think of this in terms of nines of reliability. Something went wrong, and all crypto on the internet went down to 2 nines of reliability. That's failing. So the question is, who failed? Now, Lenstra and Hughes thought that RSA had screwed up here. Like, oh my God, RSA has this thing that allowed us to go ahead and recover things when the keys were badly generated. No. Everything breaks when the keys are badly generated. The problem is that the keys were badly generated. Bad random number generations create trapdoors in all crypto systems. If instead of breaking RSA or ECC or AES or whatever, instead of breaking the thing and figuring out what key was used, you can just guess what key was used, well, that's a lot easier. And it turns out 1 out of 200 times you had the basis in order to be able to do that. So they thought that RSA was bad. They'd actually shown that still in 2012, random number generators are a problem. This is stuff that we've been fretting about for 20 years. 20 years ago, someone was saying, I hope I'm not worrying about this 20 years from now. And they're screwed. So when we found that the Debian random number generator was busted, Debian is a Linux distribution. It had some issues generating random numbers. It made a bunch of bad keys. We spent like years making fun of Debian. And it turns out it won't just Debian. A bunch of things are broken. Debian was just the tip of the iceberg. Now, weren't operating systems supposed to fix this? Wasn't the OS supposed to do all this magic work? Well, it gave us some things that we could talk to. A thing called the random device, which would always give us bits if it had it and would freeze up if it didn't. And then urandom, which would do whatever it could. Just give it something. Where would the actual randomness come from? So there's really only 4 sources of randomness that we right now really allow computers to use. We say there should be a little thing in the CPU, a hardware function that just says give me random bits, and it runs off of, I don't know, like a little radio or like bad diode, buggy hardware and made a feature. Next thing is keyboard, mouse, and maybe, okay, the speed at which the disk goes around in a hard drive, because that's impacted by air. Here's the problem. Most computers on the internet don't have a single one of these random sources. Not one. Desktops are okay. They got a human with keyboard and mouse and often some disks. Servers, less and less do they have disks. They don't have any of the rest. Virtual machines, nothing. Embedded devices, nothing. Like, not a single one of those is present. Now, people say, oh, but Intel's top of the line to be out soon CPU has a random number generator. Yes, top of the line in 2012 has finally gotten around to it. The rest of all hardware in the world that developers have to build for have nothing and will continue to have nothing. There's a rule called the high end keeps getting higher, but the low end never goes away. Now, there's these things called TPMs that are supposed to be for trusted computers and PCs. They got into a whole bunch of things in like the mid-2000s. I tell you, everything I've ever seen treats things seems like radioactive. I don't know if it's because they break stuff. I don't know because they're unstable. I don't know if it's because they may or may not be present. But they're treated like radioactive gunk, and they're almost never in embedded gear anyway. Know what I mean by embedded? Like, stuff in a rack, your little Linksys box, things like that. So what's kind of happening here, because there's no sources of entropy, let me give you an analogy. You go on the internet. Always a bad idea. Carbohydrates cause cancer. That's a real link. They'll tell you. Proteins cause cancer. Fats cause cancer. Alcohol causes cancer. Uh-oh. Ooh. Man, I didn't realize that would be a hot button subject here at DEFCON. Now, so you don't consume proteins, carbohydrates, fats, or booze. You know what happens? You starve to death. This is a thing that happens in technology all the time. You get too good at one solution and another failure mode crops up. We are starving for entropy. And the way I know this is because I actually asked some developers. I'm like, dude, what the hell? They're like, look, I got some code. It depends on the random device. I turn on my little embedded thing. It needs to generate a key. It's just born. And guess what? There's no hard drive. There's no keyboard, mouse, human, anything. It just locks up. And this is actually found during test. And it goes back to the developer. And the developer says, oh, well, let me go ahead and go to one of these not so good sources instead. The perfectionists think this isn't what's going to happen. They think the developer will protest, will march into management's office and say, buy us hardware with Ivy Bridge. We need that random number generator, damn it. No, actually, they say, freaking security people failed us once more. Let's try some crap that actually appears to work. This is reality. You can secure theory, you can secure homework, you can secure your final exam, or you can secure the frickin' internet. I'm playing the latter game here. Perfectionism caused 1 out of 200 RSA keys on the net to be easily broken. We have seen the enemy and it's us. This was our fault. This was our failure. Because we were terrified that someone somewhere might have a bad key generated on a machine, 1 out of 200 things actually did. Well, and by the way, it's worse than 1 out of 200. It's 1 out of 200 easily detectable. Way higher, slightly difficult to detect. Well, we can do better. And what we can do is we can bring back an old hack called TrueRAND. Humans and computers are not synchronized. That's why we like measuring keyboard and mice. See, the deal is, even if you were trying, you could not hit that key on a keyboard with nanosecond accuracy the same way every time. It's like, so 1/1,000,000th of a second and 1/1000,000th of a second. I don't know, whichever one it is, you ain't doing it. Any system with 2 clocks has a hardware random number generator. And it turns out the biggest lie about your computer is that it is simply one computer. Computers are small networks of interconnected devices on asynchronous networks that communicate with each other at their own time and pace. That's how they work. Every single computer has different devices talking to each other from different clocks. These clocks are not synchronized. Even if they had an error of 1 part per million, that's a bit per second per megahertz. We have way more than that actually going on. So there's an old hack from '96 by Matt Blaze and D.P. Mitchell. What they do is they run the CPU in a tight loop every 16. So they basically say increment by 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Every 16 milliseconds, they say, wait, how far did it get? On that interrupt, they do some shuffling. Now, here's where the entropy happens. You have a slow clock. It's 16 milliseconds plus minus some number of nanoseconds. And then that some number of nanoseconds determines how far the CPU spun in a circle. That's where the entropy comes from. Then they do a bunch of stuff to mix it up. Shuffle it around, hash it around, and so on. This is not a bad approach. It is totally disowned. And it's too bad. Because if it had been used and it had been part of the Linux kernel, those keys all would have been good. Now, why was it disowned? And I mean, seriously, Matt Blaze is horrified that I'm pushing this stuff. I have a tremendous amount of respect for Matt Blaze, so let me tell you, I'm at least honoring his discontent. His approach is, we can't model its behavior, and if we can't model it, we don't know how good or bad it is, so we shouldn't do it at all. I understand this attitude. It's a respectable attitude. You should know how good your system is. But what it's done is it's led to a reduction of the available entropy in the Linux kernel. We used to look at interrupt counts to go ahead and get some entropy. Someone said, oh my God, you might be able to remotely do something weird that would cause this interrupt to fire 3 times more, and then we'll get all the keys, ha ha ha. No, it's just not true. So I've been writing a thing called Dakarand. It'll be out next week. It's an update to the old model. We have various modes of generators. So we'll go ahead and we'll do a sleep with the usleep command, and then we'll see how long did that sleep actually last with various clocks. We have a thing called the monotonic clock, the real-time clock. We can actually ask the CPU, how many cycles did you run? You're like a 1.5 gigahertz processor, so the cycle count goes up 1.5 billion times a second. So how many did we go through? There's an incrementer. See how many times we can increment an integer within a time period. So we say, hey, and just keep trying to go, and wait until we passed 50 milliseconds. What's your number at? There's the real-time clock. On PC hardware, anyone remember IRQs? Yo, there's still one in use, like IRQ 8. It's like hooked up to this thing on the motherboard, and it just fires whenever you want it to. You can just say, yeah, 8,000 times a second, ping me. 8,000 times a second, plus minus some number of nanoseconds. So there you go. You got one clock against another. Then there's my favorite of these, 2 threads, 1 int. All right, look, it sounds crappy. Well played. Okay, look, anyone who thinks computers are completely deterministic devices has clearly never written threaded code. Seriously, it's really true. Guys, it's hard to make a computer do things at the right time constantly. Time is the one factor of computers we never pay any attention to. We have these things called real-time operating systems that are really difficult to write because at small timescales, computers do whatever the hell they want. Nothing a computer likes to do more than screw around for 10 milliseconds. Where'd you go? I don't know. So, it's not a bug, it's a feature. We're using those properties. We're exacerbating them as much as possible, and we're forcing them to compete, thus hopefully giving us some noise. So the flow of how all this works, we take whatever bits we get. Doesn't matter how they're good, bad, whatever. We throw them into a hash. So you have SHA-256, you can just keep throwing data into it. Just whatever they are, whatever the nanosecond clock was, you throw it in raw. Why do you throw it in raw? It might be good. Maybe it's bad, but it might be good. Let's not undercount our entropy. However, we only count it if it passes what's called von Neumann debiasing. Von Neumann debiasing means you take a stream of either zeros and ones, and we get whatever comes out of the generator. We count the number of ones in there. If it's even, we make it a 0. If it's odd, we make it a 1. 0 zeros and 1 ones, we throw that away. 0 1 is a 0, 1 0 is a 1. So we're basically capturing the transitions only. Now, we've been putting lots of data into the hash, but we count that we got a bit every time von Neumann is happy. We also throw a 0 or 1 in there just for correctness sake. Once we have 256 bits, we finalize the hash. We have a 256-bit hash now. Now we can go ahead and we run something called scrypt. script is a time memory hard function. What it means is you've got some value, you're going to spend a second churning on it until you get another value. It's just that when the bad guy tries to go ahead and do this, they got to spend a second on every single attempt. Finally, once we have this thing, we put it into encryption function AES-256 in counter mode, we get a stream, and that's the result of, that's our entropy that we're looking for. So you want to mess with this. Actually, anyone here want to mess with this? Think they can break this approach? Good. Try. You pick the hardware. You pick the platform. You pick the generator. There's 7 of them. They can't all work. Something here must fail in some environment. Here's where you can look. User space and hypervisor scheduling. So it turns out all this stuff is not running in the kernel yet. It's running as a program. Program is only visited some number of times a second, not at random intervals. So that might screw up my clocks. A bigger issue is what's called auto-clocking. If you time something against itself, you're going to have a bad time. Okay? Clocks tend to be highly correlated against themselves. So let's say you're in a VM and the real-time clock is being emulated, and it's the same emulator that's running the clock, monotonic clock that Linux is ultimately depending on. Then you might have an entropy problem here as well. Virtual machines, more than anything else, should not have to directly use this stuff. They should be able to ask their host, give me random bits. And maybe it does this stuff, but it's the host that's doing it. So, that being said, I've run this on every VM I can find, and it survives just fine, which is kind of crazy. What about VM cloning? Everyone worries about virtual machines being copied. See, here's the deal. Normally, you only get bits for your random source in the operating system really slowly. So you make a copy of this virtual machine. The pool of bits is exactly the same. You go to pull some out, you get the same bits. My approach says, look, you get different bits every time you go to the well. So each time you begin a unique read to my version of randomness, then you're okay. Now, if your virtual machine goes ahead and it's cloned before I can't, or after I can't help you, but before, you could be like right before the instruction that you say, give me some random bits, and you'll still be fine. Okay, what else could go on? Is the underlying use of cryptography safe? Well, we have this thing called, I'm called modified von Neumann. We absorb a tremendous amount of low quality data into our hash. We are throwing crap in there. But here's the deal. I hate you so much right now. You didn't realize you had one in your hand. Good man.
You're supposed to do it with us. I'm sorry, by the way.
This was supposed to be a 2-hour talk. Oops. Yeah.
He started early.
Less yapping, more talking. All right, so check it out, guys. You got 100 gigabytes of zeros. You got 128 bits of good, high-quality data. And you hash all that, generally we consider the entropy of the resulting hash to have 128 bits. Meaning you can't get worse, but you might get better. So I think modified von Neumann's going to be okay. The fact that I'm emitting the result of a pseudo-random stream instead of the raw output of a random number generator, I seem to note that every attack against random number generators involve looking at large amounts of output from them. So you know what I want to do? Not that. It seems to be the way you break these things. Maybe we shouldn't expose the raw data from our generator. It gets us busted. In fact, I wanted to see just how true that was. So normally, random number generators don't use cryptographic functions. This is a mistake because they're just as fast and we keep having security bugs. Someone found at Black Hat that, you know all those like forget my password tokens, the URLs or whatnot? So generally those tokens are generated by one of the random functions in PHP. Really? Millions of sites have bad forgot my password token generators because they're using any generator but the OpenSSL one. So the question I had was, can you actually trust a output from a cryptographic stream to survive random number tests? I mean, I assume so, but let's find out. So went ahead, thanks to Jamie Schwetman, should actually sit about 16,000 CPU hours with a die-harder entropy test run across 21 ciphers with inputs of either 16 megs of zeros or 16 megs of dev-u random. At first, it looked like there was actually the ability to differentiate ciphers and so on. Yeah, data lies a lot. We eventually found the bug. There's different padding in different cryptographic functions. So long story short, the files were of different sizes. 16,000 CPU hours, and I was detecting these two files are differently sized. This is the less embarrassing way of finding out about that. That being said, we're going to release the data anyway. We're still trying to do some machine learning against it. I actually have a neat little tool. Mail me if you think it's useful. It lets you take a comma-separated file, a CSV, and just like run SQL statements on it. Just like dynamically generates a database, executes your query, and gives you statistics. So it's called C-SQL. It's kind of nice. So this didn't work and find anything, but we did it anyway. Some kernel recommendations. These are the things I'm going to tell the Linux guys to do. Dev random needs to stop blocking. It just, no. Crypt dev random doesn't block, or crypt gen random on Windows does not block. And when I actually go ahead and get all the certificates for RDP, you know what I'm going to find? 1 out of 200 of them are not bad. They're going to be fine. Don't be so shy about interrupt sources. I don't care that much about interrupt counts. But when your network card is talking to your PC, is talking to your CPU, it is not going to be nanosecond accurate to where the CPU is. That's just not how it works. So you actually have this thing in Linux called ftrace, a really nice framework for tracing when events happen in the kernel. Right now it's microsecond accurate. Make it nanosecond accurate, and then occasionally, randomly, use values from there to seed randomness. This is the appropriate approach. Maybe consider modified von Neumann, but really, the time is over for these classes of entropy starvation vulnerabilities. It has to stop now. So, that being said, our biggest problems in security do not revolve around random number generators, just some of our more annoying ones. They revolve around languages. So we got this thing called language theoretic security, which is the idea that security vulnerabilities are the consequences of the languages that we're writing stuff in. Coined by Len Sassman and Meredith Patterson. Has a corollary: if language got us into this mess, perhaps it can get us out. One way of looking at language theoretic security is through the lens of computability. It's saying, you just want to be able to declare some information, but something bad happens and now you're running these big programs of a complexity called Turing completeness. This is a valid lens to think about. But I'm going to give you another one. Who remembers diagramming sentences? Who would have thought failure to understand this would cause the majority of all security vulnerabilities ever found and ever written? Turns out diagramming sentences is serious business. See, when you have injection attacks, that means SQL injection, that means cross-site scripting, that means pretty much every web vulnerability out there. What these attacks actually are, when you get down to it, is that one piece of the system thinks it's sending data, the other piece thinks it's receiving code. One piece of the system thinks code is coming from another program, the other thinks it's coming from the user. So everything is about tree differences. This is what's going on. You have two different trees for all injection types. Now, so what? Why am I bringing this up now? Why another theory? Well, this simple stuff is kicking our ass. This is the majority of vulnerabilities. We haven't fixed them. If we did fix them, they wouldn't still be costing us billions of dollars. So this gives us the rules of the game. If we wish to fix injection vulnerabilities, we want to synchronize parse trees. That crap of mess that you saw earlier needs to be the same on the front-end web server and the back-end database server. They need to see the same thing. And more importantly, we want developers to actually use what we write. Okay? A language unspoken has a term. It's called a dead language. So what's neat is that this approach explains what's not really well understood. Why did XML become popular? I mean, it was like this big, huge, oh my God, XML is going to save the world. You know why? It's because developers looked at it and said, wow, if I use this, I don't need to spend 4 months finding out if the third bit of the fourth byte needs me to change my parser entirely. That was life in the early 90s and is life in a couple regions of the market. Why did JSON become popular? XML figured out its own ways to get fiddly, to be honest. JSON just worked. You evaled it, move on with your life. The hard truth is that developers are in charge. It's not me, I'll tell you that much. It's not architects. They love ASN1 and XML and web services. Not academics. They love Haskell. Not management. They love money. Performance, reliability, maintainability, features, rapid developments. These are the things that make you money. Security may lose you money later. So management doesn't give a crap. They just say, do what works fastest and best by these metrics, which oddly and notably don't include security. So what is the number one thing that developers like? Code needs to work. And that's why PHP is so damn popular. Anyone here not think PHP is the most popular language on the planet? Because there's like a river right there, and I encourage you to figure out which one. PHP is really good at copying and pasting code, which is a thing, of course, no one would ever do, but everyone always does. You know, you go to the documentation, you have some tasks like, okay, I gotta read out of the database. How do I do that? Copy, paste, done. People say, oh, well, that's the wrong way to do it. I'm going to do it in Java. I'm going to do it in my IDE, my Integrated Development Environment, which is short for a thing that moved copy and paste from the edit menu to the file menu. There is a metric of quality for languages that no one measures, which is when I try something, how often does it actually work? See, normally it's, does it fail fast? Does the compiler find it quickly? Is it discovered in test? No, devs aren't looking for code that fails fast. They want it to work the first time. And it turns out PHP is an amazing language for that. It just goes. Almost no one tracks this metric of whether it works or not. Processing does, and it's an amazing language for it. But this is why all the successful languages are the brainstorm of one guy. Like, it's Guido for Python. It's Larry for Perl. Like, there's one guy who has it in his head. Art is science before we know what we're doing. Our languages that are popular are artistic endeavors, generally by one person, supported by others, but one guy's got the vision. PHP beats your favorite language, which means if you want to fix security, which you may not, you may enjoy the status quo, but if you do, PHP is the most important language in the world to repair. So, what's wrong with it? Well, we've got these things called object relational models, where you don't even go out to a database. You never write database queries with SQL. You just use normal methods from PHP or whatever language you're in, and it just makes it work on the back end. This is amazing and wonderful, and I love seeing it. The stuff works right up until the moment where you need to ask a question. Anyone familiar with that? Who knows what language this is? Brainfuck! Check it out, guys. Brainfuck has a rejoinder. There are more things in this world broken by punctuation than just brainfuck. It not alone. Look at this. Result from $name dash arrow in $names dash arrow. 32 characters of punctuation. And it's like nested in like freaking salt. Compare that to this thing. Result equals query, select name from names where length of the name less than 5. I had 12 characters of punctuation there and huge gaps. Which would you rather write? It turns out this really matters. It turns out that SQL is a language that's really good at structured queries. This matters. Now, we got some classic things that are supposed to fix this. We got like escaping. Yeah. Does anything say we don't give a shit like a 25-character command? We got bigger problems. Escapes fail open. If you just don't write it, it doesn't matter. It's a blacklist. When's the last time a blacklist actually worked? Supposedly, we can do this thing called parameterization, where what you do is you write a template. You say, I'm going to put these little holes here, and later I'm going to fill in the holes. And this is what I put in for the first hole, and this is what I put in for the second hole, and so on. Maybe if you're lucky, you get to have alias. You're going to say, I'm going to have a hole, but I'm going to name the hole. I'll tell you what the hole's name is. So you got like this big batch of code where before you had a single line. How popular is this? Well, nobody has ever written a parameterized query in their life without a gun to their head. We know we hold the gun. Even secure code, when audited, tends to be safe things are written quickly and unsafe things, then we'll go ahead and go through all this work. We threaten to fire people if they don't write it right. That's a data point, guys. If you need to like threaten people, maybe you can make a language you don't have to threaten people. Not to mention, for some reason, databases don't particularly enforce too hard right here. There's a lot of stuff that you just can't parameterize. Go ahead and try to have a hole where select is. It's not going to work. SQL, for all of its elegance, builds this really complicated parse tree. And sometimes you get to go ahead and do stuff to make it safe against injection. And a lot of times you just don't. So I released this thing in 2010 called Interpolate. And it was basically a way of saying, we're going to let devs write code the way they want to write it, and then we're going to figure out how they should have written it, and we'll actually fix it compiler side. What we're going to do is we were looking at the fact that you say you see a string, select star from foo, where x equals $x, and y equals $y. Well, humans can see the separation between data and code. Code is everything that doesn't have a $sign in front of it. Data is everything that does. But languages were throwing this out. They were just taking the value of the variable x, putting it in, making a single string, done. Information separation has been lost forever. What if it wasn't? What if we kept this data around? And so what I would do is I'd have this alternate syntax where you use the carets instead of the $, so caret x and caret y. Then I had a function that was a code generator. And it would go ahead and it would look at that stuff and say anything that began with a caret, that's a parameter. I'll put a hole there, and I'll fill the hole. And then you have to go ahead and evaluate, meaning run the code inline that's text, evaluate this new safe function. This works. This works really well. Among other things that are scary about it, what if the developer goes ahead and puts a variable into the statement that's going into the B function? Say do x equals $x instead of my funky x. Now the attacker is one step away between an evaluation and attacker-controlled code. That B function in the middle, the text that it returns is going to be run as arbitrary code. It could look at what came through and say, maybe I can predict what PHP is going to do when it runs this code. Yeah, that's a bad idea. That's not going to work. Predicting what some other language is going to do given arbitrary input is a fool's errand. So this is what we're actually doing. And Daniel Zula, who has an amazing talk coming up on Sunday, by the way, has actually implemented this. The thing that does what's called a self-scope function. Self-scope functions actually run and have access to all the variables from where they were called. This is heresy in language development. It's also a really good idea. So The idea is that we have this function MySQL safe query, and it says select star from foo where x equals caret caret x and y equals caret caret y. Inside that function, it can get the variable for x, and it can get the variable for y, and now it can go ahead and pull that out, make them holes, make it a parameterized query, and run it just like. So the dev runs this, and the code does what it's supposed to. That's kind of cool. What other things could we do? Well, there's some arguments for code rewriting. If we know what devs should write, why don't we rewrite it once and be done with it? Has anyone here ever audited auto-generated code? I'm just not a fan. There's a tainting approach that Zula's been thinking about, and I kind of like it. The idea is when characters come in from the web, you mark them as these are web characters. So as they flow through the application, they're always marked as having come from the web, and then your MySQL safe function says, wait, anything that came from the web is data, that's what I'll parameterize. It's kind of a variant on tainting. So this is kind of a neat thing that can work. I've been working with the guys over at Etsy, who have a hilariously good security team. What we've been talking about is based off a variant of what they're already doing, where instead of doing magic underlying stuff underneath the character set, expanding the object of what a string is, we just hex encode the stuff. Just like we would in HTML, and whatever 41 for an A. And now you go all the way through the application, you get to the MySQL query, it goes to execute, it says, aha, here are some hex bytes, these are parameters that came from the web, we'll go ahead and parameterize those. This work could also even be done in MySQL itself. We can modify the parser in MySQL when it got bytes that were marked in such a way they could only be treated as a string and could never be understood as code. The final alternative is actually kind of interesting, and this is really a last-minute add. Instead of marking the dangerous stuff as dangerous, we mark the safe stuff as safe. So you actually mark all SQL code using some sort of a marking, even if it's just hex encoding. Now, the reason you do this is because the bytes from the network flow through a web application 83 ways from Sunday. They're transformed. They're moved from function to function to function. This is why we have these things called static analyzers. They got to track all this crap. But the actual code, the SQL, that tends to be right before the actual execution. So that is a thing that we could do. We could mark the actual SQL and then let the other stuff go raw. This is not a bad thing. That's what langsec means. What are people trying to express? How can we make it easier to say this? What errors will people do when they try to use our stuff? If you don't care about the crap that you're putting developers through, why the hell should they care about you? So we got 2 more things to talk about. I think 20 minutes left to do it.
18.
20 minutes left to do it. Suck it. 20. It doesn't matter what code you write if there are parties in the middle that are blocking what you send. Content alteration and blocking is actually becoming a bit of a thing. Verizon's claiming the First Amendment right to edit your First Amendment rights. Entire countries are blocking web pages. It'd be nice if we could figure out what's going on here. So last year I wrote a really, really fun piece of code called Neuter. It did some crazy under-the-surface mad packet tricks to impersonate a stream between some client and some test node out there on the internet. I could go ahead and impersonate any protocol, any host. It was brutal. It would find everything. Unfortunately, it required, because of its low-level packet nature, I basically needed to ship hardware, an actual physical box that would sit at some customer site. Has anyone here ever shipped hardware? You guys are smarter than I am. That is a miserable experience. You know what's way easier than shipping hardware? Shipping web pages. That's pretty cool. So, what else could we do? We could ship executable code, set up that exe install. Uniprobe takes that approach. There's a web page approach using iframes. So you get a little window and says, in this window, do you see this website? Herdict does that. It either needs user cooperation or a Chrome extension. Is it possible to determine whether content is up or down based on nothing but a web page? So can we crowdsource censorship data? If we wish to do this, that means we want to maximize the data we get per user. We want to minimize the installation load per user. Okay, what can we do? What can we do? Well, the browser same origin policy usually prevents web pages from doing much to read one another. You wouldn't want Yahoo able to read your Gmail just because like the two windows were open at the same time. But there is one exception to this same origin policy, and the exception is images. Domains are allowed to load images from one another. Beyond that, they're allowed to know that a load was successful, not merely that there was a particular file at a location, but that it was an image, the image rendered, and here's its dimensions. You can actually learn quite a bit. Now here's the thing, if a website is being censored, images from it are not going to load. Now, what one image is on like every domain on the internet? favicon.ico. This is this little icon in the upper left-hand corner of your tab. It used to be for bookmarks. That's why it was called favicon. Pretty much everyone's got one of these. So what we do is we try to load the thing, and if it's there, great. And if it's not, we say the site is blocked. So we got this site. It's actually up to date. I wrote it with Joseph Van Geffen and Michael Tiffany for the Wall Street Journal Data Transparency Hackathon. And it is themed like Minesweeper. If you hit play, if the image loads, it will drop the favicon. If not, it will drop a bomb. Works kind of nicely. So, what's going on behind the scenes? You create an image object in JavaScript. Image equals new image. You create an onload handler. You create an on-error handler. You do this a bunch in parallel, reading from a list of sites that have been validated to have favicon.ico files. 6 failures are required before a bomb is dropped on the map. Is this enough? No. No, it's actually not. Web browsers provide really crappy feedback into what's actually going on their network stack. It's like flow control really doesn't exist. They just assume they have infinite bandwidth. My friends told me this was true when they were doing stuff still on modems. I didn't believe them. They were right. For actual reliability to the point where we could have genuine worldwide monitoring and trust the data we're getting back, we basically need to shut down all other probes while doing final validation, and then do a probe just for something that is known to be up and might be down. And even then, we're going to have a few tenths of a percent that are going to be wrong anyway. That being said, Sensor Sweeper does work pretty well. Can we do better? All right, well, let's talk about Flash and its sockets. Once upon a time, 2007, you could go ahead and you could turn any web browser you wanted basically into an open proxy to the internet. You could just basically say, hey, web browser, go to this site, get me this content, speak this protocol. It would do it for you. It was a bug. We got it fixed. However, networks are more complicated than they may appear at first. We fixed the browsers, we fixed the plugins so they can only speak back to our own IP. However, there are boxes in between the web browser and our own IP. They're called transparent proxies. Coincidentally, censoring systems are often implemented with transparent proxies. So what this means is that we actually have a thing that is nicely placed for us to start probing. Because what we can do is we can use Flash, or Haxi, which is the better language to code Flash in. We create a connection back to ourselves on port 80. And then we tell ourselves, hey, I'm looking for Facebook, I'm looking for YouTube, I'm looking for BitTorrent, I'm looking for all this stuff. And it's coming back to our IP address, but it's intercepted by the transparent proxy. The transparent proxy decides to host whatever the heck it wants. It sends it back to our Flash application, and then we can see the content and go from there. Cool. So, going beyond that, and I have 13 minutes. I'm watching this clock. You're not taking it from me. So, just as HTTP traffic on port 80 is hijacked, so may HTTPS traffic on 443. So it turns out not only can you get web content, you can go ahead and see what certificates are being changed. Turns out, when you make an SSL request, you can actually name the site that you would like. The IP at your side can actually decide based on what you said. It can either pretend to have that certificate, or it can even proxy to the real Facebook, the real Yahoo, or whatever. The transparent box in the middle that may or may not be replacing certificates, it doesn't know that it's not actually talking to the browser, so it goes ahead and provides the certificate. And that goes to the Flash applet, and the Flash applet can go ahead and bust you. So it's kind of cool. Normally, the browser DOM, when you ask the browser, it can't tell you what certificate was at a given site. So this is actually the first mechanism that'll tell you, for this site, what cert is there. There's a limitation. If the hijacking is at the DNS layer and not at the IP layer, then you won't go to the correct IP address to get the interspersed certificate. So I am not going to be running the big certificate databases, but unnamed parties who are will be getting this code, and I'm sure lols will be had. Full proxying is also possible. I'll kind of skip past this, but you can basically route every single protocol, have like a full HTTP proxy bouncing from a server through a client back to a server. Why would you do this? Because while I could try to emulate all the weirdness to play a YouTube video stream over a Flash application, it's a lot easier to just have a real browser really play through the Flash side. So that's kind of neat. So the last thing I want to talk to you guys about is scanning networks quickly. There's a thing that everyone should know. It's my definition of actionable intelligence. What can an attacker do today that he couldn't do yesterday for what class attacker to what class victim? If you write an advisory that does not answer this question, it's a bad advisory. What changed? And a big part of determining how big deal a bug is, well, how many systems actually have this bug in the first place? I've run 2 major scans for 2 major press announced bugs this year. One was the telnet encryption bug. One was the RDP attack. And the question was, were either of them widespread? Telnet, nowhere. There's like a tiny, tiny number of hosts that are running it. RDP, yeah, like 5 million hosts were running that. That was actually a big deal. So this is important. If we're going to actually rationally respond to bugs, we should know, does anyone actually have them? So how do you actually do these scans? Once upon a time, I wrote a network scanner called ScanRand. It was fast because at the time I didn't actually know how to slow down. I just kept running in a loop and it worked. So I sent a bunch of connection requests called TCP SYNs. This is now not enough. There are a whole bunch of things that will respond to the SYNs with the proper SYNAC, but nothing is there. They answer the door, but nobody's home. So you basically have to split your process. You get a bunch of candidates through the old method where you see if the 3-way stuff actually works. And then, only then, you go ahead and you do real connections and connect to the IP. So a little bit more detail, you send the SYNs, you increment the first byte first. The reason you do this, so 1.1.1, 2.1.1.1, and so on, this means the larger the network you're scanning, or the larger the internet you're scanning, the slower you're scanning each individual network, because you're spending your time somewhere else. So it increases your success rate. Then a separate window, I don't even use ScanRand to go ahead and capture the data. I actually have TCP dump capturing syntax. Neat little command that'll do that. And then once I have my candidates in the telnet encryption case, the Nmap guys were so kind. They went ahead and whipped up a quick check for me. And I just fed my IP list to it, and very few were found. When I was getting RDP, there's an excellent framework called Black Mamba. It's at rootfoo.org. You basically just write really simple, straightforward code, and every time you're going to stop in the middle, you yield. So you say, yield connect. So come back after you get a connection. Then come back after you're able to write these bytes. Come back after there's a response. And Black Mamba makes it work very, very nice. This gives you about 3,000 IPs a second. I want more. So I've always wanted to write a user space network stack. This is a program that directly talks to the network and retrieves content. HD Moore kind of kicked me into high gear on it. He's got some mysterious new scanning project called Critical I/O. I am not at all beyond supporting any crazy project by HD Moore. Heck yeah. So ScanRAN 3 will be out shortly. ScanRAN 3 is a new scanner. It doesn't just flood SINs, it actually connects to nodes and extracts data. The original plan was to have there be a database inside of ScanRAN. I was going to use SQLite. Why? Because I thought it'd be funny, just humorous, to have a network stack where I'm like, select star from sockets where data sent not equal data acknowledged, and data sent time minus now is greater than 3. So it'd be like a database lookup to figure out where you needed to send a retransmit. That would be cool. This was useful for SQLite, because that's really, really fast. If there's no index. That speed disappears if you add indexes. So if you actually want to be able to query the database, SQLite is no longer fast. So let's just not do that. Can't someone else do it? So check this out. I didn't think this was possible, but it actually works. ScanRAN did not get its speed by keeping track of all these machines it was speaking to. So why should ScanRAN 3? We're going to build a stateless TCP stack. It just sends data, it doesn't remember to who, and the other guy remembers that he's talking to me. Thanks. The way you do this, you send a SYN, and you set the maximum segment size and window size to 1460. What this means is at any given point, there's only going to be one packet outstanding at a time. So now whenever you receive a SYNAC, okay, you got to talk, you send your payload, you send the acknowledgement. Every time you get another acknowledgement with a payload, you acknowledge that, you ignore if there's no payload. And when you get a FINAC, you send a reset, you say, I'm done with you, don't remember me anymore. In every situation, except for if the original SYN is dropped, every time the other side sends a packet, if there's a drop, well, whatever, he'll clean it up for you. I can take 3.25 million IP addresses. I can sweep them from my little $200 Opteron box on a really nice pipe. I can get 800 megs of HTTP data. The scan takes 75 seconds. And of course, this is not even optimized code, right? This will get out to about 200,000 IPs a second. You end up doing stream reconstruction with a SQL query, which is kind of fun. Security, right now I've implemented none of it, just like your average developer. For security, you basically put cookies into the sequence number and source port, and maybe the TCP timestamp. So the idea is you can put little secret data so you know when someone's responding to you, they're actually responding to you and they're not faking responses and, saying that Google's got a bunch of spicy stuff. Some notes. This may not be necessary. Kernels have gotten kind of fast. Non-blocking connect plus epoll should probably be able to do at least tens of thousands of sockets per second, and it'll certainly be easier to code for. But my approach eventually becomes the fastest because I'm just really lazy. I'm not doing anything. The other guys are. The biggest performance advantage that I'm going to get is when I get what's called a write V for write vector, where I can give the kernel a whole bunch of packets to send instead of just one. A couple more notes. I can try more efficient stores in SQLite. I can do a giant allocation of RAM and just have fixed offsets per IP. There's a cool project called MemSQL from these old Facebook guys. And they're basically converting SQL to C++. So that might actually work. We'll find out. And there are merged approaches too, where I only keep state if I get a certain distance into a session. Now, there are a few servers on the internet that do not actually have a state either. They say, well, the client will keep track, and I'm almost done. These servers tend to be run by Google. And yeah, if a client thinks the other guy's going to do it and the server thinks the other guy's going to do it, it's a bad day. The most important feature to write that isn't written yet, I need to implement blacklist support. Most networks don't complain when you scan them. Those that do, you gotta honor their request. And it actually does require a fairly efficient data structure not to go ahead and have that take all your speed. Don't mess with the firewall. Just have your code get its own IP. Your little program arbs for itself. And that's lots of stuff. I hope you like it. I'm out.